It's a pleasure to have Patrice Meunier, who is going to tell us about instability of a columnar vortex in a stratified fluid. He's from Marseille.
Thank you. So yes, this work has been done at our lab IRFE, which is Institut de Recherche sur les Phénomènes Hors Equilibre in Marseille, in France. And the work has actually been done by two PhD students, which are Xavier Ridinger and Nicolas Boulanger, who are supervised by myself for the experimental part and by Stéphane Ledizès for the theoretical part. And some of this work has also been done in collaboration with Paul Billan for the final part at Lady X or Ladix, I don't know how you want it to be pronounced. So the idea is to, we are exactly in the same idea as this morning's session about the instabilities of a tall columnar vortex. So why do we study these tall columnar vortices? Well, we all know that there are a lot of vortices in turbulent flows. However, it's true that in stratified flows, they are usually more flat, like pancake vortices. But in laboratories, it's easier to create some tall columnar vortices. And also, it might be found, for example, if you have a coastal tip here, you have some generation of vortices which are shaded behind this tip. This has been found by Paulak et al. And these vortices are strongly tilted with respect to the stratification. And also, this is more relevant to tornadoes, although there are a lot of actual velocities inside these tornadoes. This is more relevant for the case we are looking at. And here also we can see that there is a strong tilt. So we started to wonder what would be the idea, what would be the influence of this tilt when you have a stratified fluid. So I will just describe the system and the experimental setup, and then I will mostly talk about the tilted vortex here, and then in the second part I will talk about a vertical vortex, which is in fact more difficult. So we have a vortex, a stable vortex. It's not like the centrifugally unstable vortex like this morning, because we have here a Gaussian distribution of vorticity. So it's very stable compared to the Rayleigh criterion. And this stable vortex is tilted with an angle alpha with respect to the stratified fluid with a Brent-Weissala frequency n. And this is a linear stratification. The vortex is characterized by this Gaussian profile of vorticity, which has a circulation gamma here and a core size A. In the theory and in the numerics, we will suppose that it's a constant in time. However, in the experiments, it is evolving with time due to viscous diffusion. But if we look at very strong instabilities, then we can neglect the viscous diffusion. So we say that the core size is frozen. So there are three parameters for this system, which are the Reynolds number, of course, which is based on the circulation of the vortex, the Froude number, which quantifies the angular velocity of the vortex, which is gamma over 2 pi a squared, divided by the Brent-Weissala frequency n. And then the angle of tilt, which is varied between 0 and 30 degrees. We did not go further. We have done an experiment in this tank here, which is full of fluid, which is salted water. And it's a linear stratification, density stratification, with a buoyancy frequency which can be varied between 1 and 3 radians per second. And the vortex is generated by this flap here, which is impulsively rotated in the fluid. This makes a very nice vortex that you can see here, which can be visualized by dye. If you put some dye at the edge of the plate, then the dye is going to be advected inside the vortex, and it's a very nice way of visualizing the vortex. But we have also done some PIV measurements in order to know exactly if the Gaussian vortex is really Gaussian, so to look at the vorticity profile of this vortex. And we have also done some shadow graph visualizations here, which are made by placing a small lamp here and looking at on the other side through a lens, which allows to see the density gradients of the fluid. I'm going to start with this tilted vortex. And this is a shadow graph visualization. This is a movie. So we have to imagine that the vortex, the plate is here. It's slightly tilted with 4 degrees, I think, or 8. And we are going to move the plate like this so that the vortex is going to be generated here with a slight tilt with respect to the vertical. So what happens when we launch the plate? We can see the vortex here that is created, and then suddenly you have a very, very strong instability. Let me try to do it again, because there is something at the beginning that I would like you to see. You have 2 bands here, and this instability starts from these bands and creates a very strong mixing of the vortex. So to summarize, at first we can see a critical layer, or these 2 bands here of white and black in the shadow graph, which lead to a very strong instability, a 3D instability, and then this 3D instability creates a very strong mixing. So how can we understand this? Well, let's start by the beginning. We will start by this critical layer. I will show that it is a critical layer. If we look at the radius where these bands appear, and if we plot this as a function of the Froude number, the inverse of the Froude number, well, we can see that this radius is exactly where the angular frequency around the vortex is equal to the Brun-Weisseler frequency. So there is some kind of resonance of the motion at this radius because it's equal to the Brun-Weisseler frequency. In fact, this thing has been already observed by Carito and Flor, and this instability had been already seen by Carito and Flor, although they didn't have any intentional tilt. So they had a vertical vortex, but now they admit that, you know, with some small perturbations, it might be slightly tilted for a few degrees, and that was enough to create this critical layer, and they even saw the same instability. So it's a very strong instability. So why do we have this critical radius where you have a very strong density gradient? Well, it's quite easy to do the theory by doing an asymptotic expansion at small tilt angle alpha. So we assume that there is a Gaussian vortex, which is modeled as this velocity u0, and we add a perturbation u1, which is proportional to the tilt angle. Well, in fact, we had to do a change of variables to solve the problem because it's not very appropriate. So at order 0, it's the Gaussian vortex. And at order 1, if we put everything into the Euler equations, we can show that the solution is 0 on the radial velocity, azimuthal velocity, and the pressure. But it has a strong, it has a component in the vertical velocity and in the density here. This solution is, of course, with an azimuthal number, wave number m equals 1, because the forcing is an azimuthal number m equals 1. And then this velocity, there's something strange that appears when the angular velocity here, omega, which is defined here, is equal to the Brun-Weisseler frequency. So we recover here that when the angular frequency will be equal to the Brun-Weisseler frequency, then the velocity is going to diverge. And this means that this solution breaks down at this critical radius. I have to note that this can happen only if the Froude number is sufficiently large, so larger than 1 here, such that the angular velocity can be larger than the Brun-Weisseler frequency. At very small Froude number, omega is always smaller than n. So to solve this critical layer, well, we have to add viscous effects. That's a rather standard analysis. And we can show that the viscous critical layer analysis will show a scaling as Reynolds to the 1/3 for the amplitude, but also for the size, the width of the critical layer. So we do this change of variables using this Reynolds to the 1/3. We put everything in the Navier-Stokes equations, and we do a local analysis around the critical radius, and we find an error equation for the velocity, with a forcing term such that the solution is a scorer function. Anyway, that's an analytical solution. And thus we know the velocity profile inside the critical layer. This is shown here. That's the vertical velocity inside the vortex. It has a rather strange shape, but experimentally that's exactly what we find. If we measure the vertical velocity, it has exactly the similar shape. And if we try to understand what is this critical layer, if we do a section here, we have a strong positive jet here, and a strong negative jet here. And that's exactly what we find experimentally with here the circles at exactly the critical radius, and on the other side it's negative. So it seems that this theory is working quite well. If we look in the other section here, well, it's not a jet, because here we have, in fact, a strong shear here. And the same shear here is not opposite. It's in the same direction on the other side of the vortex. And experimentally, we recover these shears. So these shears are of order alpha Reynolds to the 2/3, because the width of the critical layer scales as Reynolds to the 1/3.
What's this function, HI?
Scorer's function.
Scorer.
Scorer's function. Yeah.
Are you free to set alpha? It's not an exact solution, is it, if you include any alpha?
We neglected the nonlinear terms, but in fact, all the nonlinear terms vanish. We did the nonlinear critical layer analysis afterwards. I mean, it's often adjusted, and in fact, all the nonlinear terms vanish. So if the perturbation is smaller than the base flow, then everything vanishes. So it's a solution up to the perturbation equals to the base flow. That's weird. It's impossible to do a nonlinear critical layer analysis. That's weird, but it's like this. So now let's go on, because we know the base flow. Now we're going to try to understand this instability. We can see that this instability starts exactly at these critical layers. And we know the flow there. So we're going to try to understand how it could lead to this instability. I mentioned that it's exactly identical to the Carreto and Floor instability. And it seems to be, if we look at this picture, it seems to be a helical secondary vortex that is wrapped around the primary vortex. But in fact, it cannot, because it's rotating in this sense, so like this, on this part, and in the same sense in this part. And that's impossible, because if it was a helical vortex, then it would rotate in this sense, and in the other sense on the other part. So it's not a helical vortex, it's rather some kind of vortices that are created by this shear instability. So we will see much better here in the PIV measurements. That's a cross-section of the vortex, and we can see these two shear layers, which are simply the solution of the critical layer. And when we do some PIV, we can see that these shear layers destabilize due to a Kelvin-Helmholtz instability. So in fact, this 3D instability is simply a local instability of the shear layer created by the critical layer. But I said also that the critical layer has two jets, one positive and one negative, and a jet is also unstable. So if we look in the other section, and if we do PIV measurements, we have that kind of instability, which looks more like a von Karman alley, or it's exactly the sinuous mode of the jet instability. So it seems that this instability is directly linked to the flow inside the critical layer. So we try to do a linear stability analysis by adding a perturbation superimposed to the Gaussian vortex plus the critical layer solution due to the tilt, which is proportional to the tilt angle and to the Reynolds to the 1/3. So inside the critical layer, we put everything, the base flow, the critical layer flow, and this perturbation. And we linearize around this. So there are a lot of terms. I don't want you to understand all of them. There are many terms, but we can neglect most of them. For example, this term is as 1 of the Reynolds to the 1/3, so it's negligible. And many of these are negligible. There are just a few terms that we have to be careful about because we have to assume that the advection around the vortex is small enough such that the instability grows without the advection to be efficient, such that the profile is always the same profile. Because here it's a shear, here it's a jet, so we want to freeze the profile, the velocity profile. Anyway, if we neglect all these terms, then we get a very simple equation because it's simply the Rayleigh equation. So we found again that it's the velocity profile inside the critical layer that is going to govern the instability. And if we put here in W the profile of the critical layer, either the shear or the jet, then we can do some basic numerics to look at the growth rate. And we can show that the growth rate here, as a function of the wavelength, is like this for the shear layer profile and for the jet profile. Well, all these experimental measurements are in good agreement for the wavelength and also roughly for the amplitude of the growth rate, even if there is a lot of dispersion. So it seems that we can understand why it is unstable. It is really linked to a local instability of the velocity profile inside the critical layer. And if this is true, then it should be unstable when the fluid is larger than 1, because if it's smaller than 1, there is no critical layer. And it is unstable when this, which is the shear, the amplitude of the shear, is large enough. That's roughly what we find for this frontier. And that's exactly correct for fluid larger than 1.
So you really can neglect the stratification in your shear layer instability of these vertical flows.
That's
a bit surprising.
yeah, but it's a negligible term. In the Boussinesq approximation, it's a term which is linked to, I think that's this term.
Your unstable eddies are much faster than n to the -1.
The variation of the density is very small in the radial direction. So there is no related or instability. At first, we also thought that it might be that kind of instability, but it's related, I think, to this term. Yeah, this term, and yeah.
So the eddy
So
timescale must be much faster than the buoyancy timescale. It's the only way this could be true.
Than the radial buoyancy term, yes. Not the vertical, the radial buoyancy term.
Slight tilt.
Yeah, it's a very
Vertical
small
motion
tilt.
is important.
It's a asymptotic analysis, so it's for small tilt. Everything will break down when we have finite tilt. I agree. Okay, so I have 10 minutes, well, no, 5 minutes. Well, the funny thing is that this instability is not destroying the vortex, because if we look at the circulation here of the vortex, even if it's unstable, then the circulation is not destroyed. It doesn't go to 0 because it has some angular momentum. So you cannot destroy this vortex. It always has its angular momentum. However, it can largely increase the core size here, A, of the vortex, and then the fluid number decreases because it gets larger. And this way, you have all the vortices that have a fluid number larger than 1 that would go under the limit of fluid number 1. So that's something interesting. All the vortices that have a fluid number larger than 1 would be unstable and get to fluid number smaller than 1. Well, that was for a tilt. I'm going to talk a little bit about vertical vortex. Well, here we don't have this critical layer because the angle is exactly equal to 0. So what we did, I mean, Paul Billiat and Stéphane Ledizès had shown that it would be unstable due to radiative modes. And we wanted to, but this theoretical analysis was at infinite Reynolds number and at very large K analysis. So we wanted to do the linear stability analysis. So that's a numerical linear stability analysis. We decompose the velocity using a normal mode decomposition. We put everything in the Navier-Stokes equations, and we thus have an eigenvalue problem for the frequency, such that the boundary conditions are met at infinity. The problem is that the modes that we want to find are radiative, so they extend up to infinity. And this is not correct if you use some Chebyshev polynomials. So you have to use a trick to put the modes localized in R. So the idea was to change the radius in a complex radius here using a small complex argument phi, which is very small. And this transforms an oscillating mode in a localized mode due to this part here, which is exponentially decreasing. And this does not change the frequency, so we can solve numerically the problem. And this is what we get. That's the growth rate here. Omega I is the growth rate of the mode. When you have a vortex which is stable with respect to the centrifugal or inertial instability, but these modes are oscillating very far from the vortex. Sorry, and this vortex is very small. This growth rate is very small. You can see that it's 5 × 10⁻³ compared to the angular velocity of the vortex. So it's very small, and that's why maybe it's very hard to find experimentally. It can be unstable for all azimuthal wave number, but it's most unstable for m equals 1. And it's unstable for any Reynolds number, even for very small Reynolds number. This was very striking. And it's always unstable in a band of Froude number, which is around 1. We can understand that because if we increase the Froude number, then you get to non-stratified vortices, which are stable. This we know. And if you go to very small Froude number, well, you can show that the wavelength of this unstable mode is scaled as 1 over the Froude number. So when you get to small Froude number, you in fact have some very large wave numbers. And if you have some very large wave numbers, then you have viscous effects very strong. So in fact, at finite Reynolds number, it's a viscous stabilization at small Froude. That's something weird. This is the structure of the mode. Here, it's like a non-stratified displacement mode here. And then you have these edges that are the radiative structure of the mode. And this is like internal waves that are emitted from the vortex. So that's the global structure of the mode. However, when you increase the Froude number, there's something that appears. It's a critical layer, again, that appears in the mode. And this critical layers increases and makes the growth rate decrease. So it kills the instability when you increase the Froude number. So that's how you get from the stratified vortex to the unstratified vortex. And when you increase even the Froude number, then the growth rate as a function of the wave number, the curve seems to be different. At first, you have some kind of all wave numbers are unstable, but when you increase the Froude number, then you have bands of instability with very specific wave numbers. And this is in fact due to a different mechanism, because at low Froude number, you have these radiative modes that are unstable. They get stable. However, they can interact with the unstratified modes, which are known as the Kelvin modes in vortices. And if you have a resonance between these two modes, because they share the same frequency, omega r, then at intermediate Froude number, you can have a resonance between these two modes, which leads to bands of instability here. So that's a different mechanism. It's not these modes which are unstable. It's something slightly different. Experimentally, we've spent a lot of time trying to find these radiative modes. And it's very, very tricky because you don't want the zigzag instability that Paul Billion talked about this morning. And it's very hard because you always do a stopping vortex when you stop your plate. So we spent almost 2 years trying to have only one vortex, and you always create a second vortex. I think that now we have roughly the correct instability. We had to use a very large plate here, such that all the vortices would be very far away. They are more than 10 centimeters away. So that's what we find. It's not very clear, but we think it's, so the vortex is behind the plate. Now you can see it, its axis is here, and you can see that it's slightly undulated. But the instability is very weak. It disappears, then reappears. It's not very clear. So I show you this because we think that it's the correct instability, but it's extremely tricky to find experimentally. If we measure the wavelength here, it's 7 times the core size, and theoretically it should be 3.7 for this full number. So it's not exactly the correct value, but it's close. So that's where we are for the moment, experimentally. And I will thus conclude. So I first talked about stratified tilted vortices. And I showed that for a fluid number larger than 1, there is a critical layer which creates some strong jets and shears at this critical radius with a strong amplitude, since it scales as the Reynolds to the 1/3. And this critical layer leads to a very strong 3D instability. And I didn't mention this, but the growth rate is proportional to the alpha Reynolds 2/3 times the Brun-Weisseler frequency. So that's something quantitative that we may use in, for example, in real oceanographic flows. And these tilted vortices remain. However, the fluid number decreases and goes under 1. And finally, vertical vortices are unstable, but very weakly unstable. And they're unstable for fluid of the order of 1. And for large fluid, there is a different mechanism for this instability, and they're even weaker. So thank you very much.
Do you think your low Froude number instability with the radiating internal waves could be related to the broad-bent Moore instability of a two-dimensional vortex radiating sound waves, or Rupert Ford did a similar thing for gravity waves in a shallow water model?
Yeah, I think that's exactly the same instability, because you see these Kelvin modes that will excite these internal waves, and then these internal waves interact with the Kelvin mode. That's how I kind
of course, by Kelvin you mean what we now call Rossby, even though,
yes,
of course, Kelvin did discover it.
I come from the vortices community. Yeah, these Rossby waves, Kelvin mode. I think that's the same instability. So that's, we have to make the link.
More questions? Coming back to the tornado, they are so stable because the omega is so high compared to the n. Or what is your answer?
I think that's much more complex. There is a strong axial flow. There's the effect of the ground, and I'm not sure that stratification is very, very important there. I think the ground effect is very, very important, and you may have different axial profile inside. You may even have some velocity going down. That's something maybe completely different. I'm not sure about the stratification, if it's really, really important there. I think it's much more complex.